On March 19th, 2025, a team of more than 900 scientists working on an instrument called the Dark Energy Spectroscopic Instrument released a result that sent a quiet shockwave through the physics community. Using the largest three-dimensional map of the universe ever built, tracking nearly 15 million galaxies and quasars across 11 billion years of cosmic history, the team announced that dark energy, the mysterious force believed to make up the majority of everything that exists, might not be constant at all. It might be weakening. And if that finding holds up, it would not just tweak a number in a textbook. It would mean the fate of the entire universe, whether it expands forever into a cold, dark silence or eventually collapses back in on itself, is genuinely still undecided. That announcement is only the latest chapter in one of the strangest and most urgent stories in modern science, the hunt for two forces that make up 95% of everything around us, yet have never once been directly seen, touched, or captured by any instrument humanity has ever built. Stick with me for the next few minutes, because I am going to walk you through exactly what dark matter and dark energy are, the space telescopes racing right now to find them, and the shocking recent discoveries suggesting we may have gotten the ending of the universe's story wrong. And if you want real science without the exaggeration, go ahead and subscribe now, because this is one of the biggest open questions left in all of physics. What we see in the sky is just the tip of the iceberg. The sun, the moon, stars, planets, and galaxies, all of this visible universe makes up only 5% of its total composition. So what lies hidden in the remaining 95%? Today, the vast majority of scientists agree that most of our universe consists of dark matter and dark energy, two forces that cannot be seen or touched. Yet without them, the cosmos itself could not exist. One of them acts like cosmic glue, holding galaxies together and preventing them from falling apart. The other, on the contrary, stretches space itself, causing galaxies to rush away from each other at ever-increasing speeds, sometimes even faster than the speed of light. But if these forces are invisible, how can we possibly study them? In 2011, the European Space Agency decided to approach the problem differently. Instead of looking for the forces themselves, they would study what these forces leave behind. If galaxies cluster in one place, dark matter is likely at work. If they rapidly scatter, this could be a sign of dark energy. To test this, the Euclid project was launched, a space telescope designed to create the most detailed three-dimensional map of the universe ever made. This map will help scientists understand how the invisible forces of dark matter and dark energy shape the structure of everything around us. On July 1st, 2023, Euclid was launched into space, and it has spent the years since transmitting unique images of distant galaxies, nebulae, and superclusters, structures that seem to bear the imprints of these mysterious forces. Right now, in 2026, these observations are becoming especially important, as scientists piece together a picture of dark energy that increasingly does not match what anyone expected. Euclid has been nicknamed the cosmic detective because it is not just a space telescope capturing stunning images of deep space. It is conducting a genuine investigation into one of the greatest mysteries in the universe, the nature of dark energy and dark matter. As part of its mission, which will continue until 2030, it is set to study 1.5 billion galaxies, peer into the most distant corners of the universe billions of light years away, and in doing so, uncover the true nature of these two forces. As of early 2026, the Euclid-wide survey had already covered more than 5,000 square degrees of sky out of a planned 14,000, and the mission's first major cosmology data release, containing the results scientists have been waiting years for, is scheduled for release in October of 2026. In June of 2026, the team published a first demonstration that Euclid can genuinely trace massive structures dominated by invisible dark matter, using a technique called weak gravitational lensing, a crucial proof of concept ahead of those full cosmology results. Let's begin with a photograph of the most massive structure known in the observable universe. Scientists have dubbed this image a revolution in astronomy. It captures the Perseus cluster of galaxies, 1,000 galaxies belonging to the Perseus cluster itself, and over 100,000 additional galaxies visible in the background. Many of these faint galaxies had never been seen before. Some are so distant that their light took 10 billion years to reach us. This enormous cluster, located 240 million light years away, could not exist without dark matter. According to scientists, the visible mass, stars, gas, and dust is simply not enough to hold everything together through gravity alone. It is the invisible dark matter that acts as the glue keeping the galaxies from flying apart. One of Euclid's key tasks is studying how dark matter and dark energy influence the shape and movement of galaxies. Dark matter is like an invisible framework. It pulls in ordinary matter, stars, gas, and dust, and helps galaxies hold themselves together, a kind of gravitational glue keeping the stars within a galaxy from scattering into space. The more dark matter there is, the denser and more stable a galaxy becomes. Dark energy, on the other hand, operates on a much larger scale and does the exact opposite. It pushes galaxies apart, expanding the universe, and influences how quickly galaxies move away from each other, how often they collide and merge, and the conditions in which they continue to exist. Together, these two forces, one pulling, the other pushing, create the universe's unique cosmic pattern, determining what galaxies will look like: compact, dispersed, or vast and dense. That's why it's fitting that one of the first galaxies observed by Euclid was nicknamed the Hidden Galaxy, also known as IC 342, considered a twin of our own Milky Way. IC 342 has the classic spiral shape typical of most galaxies today, but galaxies weren't always like this. In the early universe, most galaxies were small and irregularly shaped, because they formed in a far hotter and denser cosmic environment than we see now, making their formation chaotic. These irregular galaxies became the building blocks of larger, more orderly systems like modern spirals. A galaxy called NGC 6822, located just 1.6 million light-years from Earth, and part of the same galaxy group as the Milky Way, became the first irregular galaxy observed by Euclid, and its images revealed a huge leap in detail and color resolution compared to earlier observations from the James Webb Space Telescope, thanks to Euclid's infrared instrument and wide field of view. Scientists identified numerous globular clusters in the image, ancient star formations containing thousands of stars held together by gravity, along with the most active star-forming regions of the galaxy. Euclid also captured a stunning image of a cluster called NGC 6397, located 7,800 light-years from Earth. Observing these structures in detail is extremely difficult because most of the stars are concentrated near the center and brighter stars drown out the dimmer ones. NASA's Hubble Space Telescope managed to observe the core of NGC 6397 in detail, but examining the outskirts with Hubble would take an enormous amount of time. Euclid can do this in just 1 hour. That is the same amount of time it took Euclid to capture the most detailed image yet of a massive star-forming region called the Horsehead Nebula, located 1,375 light-years from Earth, south of the star Alnitak in Orion's famous belt. Many telescopes have already photographed the Horsehead Nebula, but none have captured it as clearly and on such a broad scale as Euclid, which shows the entire nebula in full, where earlier images from James Webb and Hubble only captured fragments of it. Scientists will use this data to search for faint, previously unseen planets with the mass of Jupiter still in their cosmic infancy, along with young brown dwarfs and newborn stars, all shaped by radiation from the bright star Sigma Orionis glowing just above the nebula. Euclid's amazing capabilities began revealing themselves back in September of 2023, during its initial test runs, when scientists spotted something extraordinary in just a handful of early images: a perfect Einstein ring. Active galaxies powered by supermassive black holes feeding on enormous amounts of gas, the brightest single objects in the entire universe. The closest quasar to us, 3C273, is estimated to shine 25 trillion times brighter than our Sun. This particular map marked 1.3 million such objects, serving as visual proof of how dark matter is distributed across the cosmos, since without its invisible gravitational glue, these enormous structures simply could not have formed in the first place. The Gaia telescope's mission came to an end on March 27, 2025, when it was shut down and began its slow drift toward a final resting orbit around the Sun, closing out one of the most productive astronomical surveys in history. When it comes to dark matter and dark energy, there is still far more unknown than known. What we do know is that some mysterious force attracts and holds galaxies together, while another accelerates the universe's expansion at the same time, yet neither has ever been directly detected. If physicists had a most wanted list, dark matter would sit right at the top. It is theorized to be an invisible material spread throughout the entire cosmos, and current estimates suggest just 5% of the universe is ordinary matter. Roughly 68% is dark energy, and the remaining 27% is dark matter, the two acting almost like the yin and yang of the cosmos, one attracting, the other repelling. The mind-bending part is that these theoretical substances make up 96% of everything that exists, and we still cannot see either one because neither interacts with light or any electromagnetic force. The only reason scientists believe dark matter exists at all is because of the gravitational effects it has on stars and entire galaxies. Similar to seeing wind move through trees. You cannot see the wind itself, only its effects. The idea of dark matter is not new. The first clues came in the 1930s, when astronomer Fritz Zwicky studied a distant swarm of galaxies making up the Coma cluster and noticed something strange. The galaxies were moving so fast that the cluster should have flown apart, yet it hadn't, leading him to conclude there must be some unseen material holding it together. In the 1970s, astronomer Vera Rubin made a similar observation, finding that stars swirled around spiral galaxies far faster than expected, again implying some unseen gravitational force at work. From that point forward, many researchers became convinced dark matter genuinely exists, and numerous types of particles have been proposed to explain it, though experiments so far have only managed to rule out contenders rather than confirm one. But a newer study suggests dark matter might not exist at all, at least not in the way we think. Researchers found small discrepancies in the orbital speeds of distant stars, showing almost no gravitational effects, hinting that our understanding of gravity itself, rather than an invisible substance, might explain the gravitational strength observed in galaxy clusters. Adding to that uncertainty, an international team of astronomers studying a galaxy called AGC 114905 spent 40 hours with state-of-the-art telescopes and found it contains little to no dark matter at all, located about 250 million light-years away and classified as an ultra-diffuse dwarf galaxy. It is roughly the same physical size as the Milky Way, but contains 1,000 times fewer stars. The prevailing theory holds that galaxies like this can only exist if dark matter holds them together, yet the motion of gas within AGC 114905 can be fully explained by ordinary matter alone, with no dark matter required, even though theory predicts it should be there. Possible explanations include the galaxy having had its dark matter stripped away by a nearby larger galaxy, except there are no nearby galaxies to blame, leaving the mystery unresolved. Other researchers are chasing an entirely different theoretical candidate using gravitational waves, ripples in space-time, caused by major cosmic collisions. Scientists are now using instruments like the Laser Interferometer, Gravitational Wave Observatory, to hunt for what are called boson clouds, made of ultralight subatomic particles that are almost impossible to detect directly, but have been proposed as a possible source of dark matter. Searching for the gravitational wave signatures these clouds might produce as they circle rapidly spinning black holes. Meanwhile, another entirely different theory suggests dark matter may actually come from regular matter through a process scientists call freeze-in, the reverse of an older idea called freeze-out, in which dark matter particles colliding with regular matter could annihilate it and produce two new dark matter particles in its place, growing at an exponential rather than a gradual rate in the extreme heat of the early universe, potentially explaining the roughly 6-to-1 ratio of dark matter to regular matter we observe today, before the reaction shut off entirely as the universe cooled and the total amount of dark matter became fixed. And then there is dark energy's own strange twist. Dark energy wasn't even discovered until 1998, when observations revealed the universe wasn't just growing larger, but doing so at an accelerating rate, a genuine surprise, since all the visible matter in existence should have been pulling everything inward rather than pushing it apart. In 2020, physicists, using the Xenon 1T detector, a massive tank of liquid xenon kept deep underground specifically to hunt for dark matter, picked up a strange excess of signals, 53 more events than the expected background of 232. At first, researchers suspected a hypothetical particle called a solar axion, but further investigation showed far too many would be needed to explain what they were seeing, leading some physicists to propose an entirely different culprit, a possible force carrier particle for dark energy itself, detected completely by accident while searching for something else. Some astronomers remain skeptical, and considerably more verification is needed before anyone calls it confirmed. But if true, it would rank among the most significant discoveries in the history of physics. Directly detecting either of these forces remains one of the hardest challenges in all of science, since both are invisible and barely interact with ordinary matter at all. That is exactly why NASA's next major weapon in this hunt, the Nancy Grace Roman Space Telescope, is generating so much anticipation right now. Originally slated for a 2027 launch, the observatory finished construction ahead of schedule, and NASA has since moved the date up twice, now targeting liftoff on August 30th, 2026, atop a SpaceX Falcon Heavy rocket from Kennedy Space Center. Roman carries a mirror the same size as Hubble's, but its 300-megapixel wide-field instrument captures a swath of sky 100 times larger in a single exposure, and its mission is built specifically to measure the shapes and distances of billions of galaxies in order to map exactly how dark energy has driven the accelerating expansion of the universe across cosmic time. When astrophysicists finally do pin down what dark matter and dark energy actually are, whether through Euclid's upcoming cosmology release, DESI's third and final galaxy map, or Roman's brand new eyes on the sky, it will rank among the greatest discoveries in the history of science. So make sure to stay tuned here, because when that moment comes, we will be the ones telling you exactly what it means. Thanks for watching. This is a rare cosmic phenomenon where a massive object like a galaxy bends the light from a more distant galaxy behind it, forming a ring of captured light, an effect called strong gravitational lensing that helps scientists peer deeper into the universe than ever before. Imagine a giant lens, but instead of glass, it's gravity doing the work. Any massive object, a galaxy or a cluster of galaxies, warps the space around it, and light passing through that warped space bends just as it would through a magnifying glass. Thanks to this effect, we can see objects that would otherwise remain completely hidden, Distant galaxies that would normally be too faint suddenly becoming brighter, sometimes even appearing larger than they actually are. In this particular case, the galaxy NGC 6505, located 590 million light-years from Earth, bent the light of another galaxy sitting 4.42 billion light-years further away into a nearly perfect ring encircling it. Among the data Euclid has collected since, scientists have already discovered 500 new examples of gravitational lensing, and by the end of the mission in 2030, that number is expected to exceed 100,000, roughly 100 times more than currently known, all while 2,000 scientists around the world work to analyze the data and unravel the true nature of dark energy and dark matter. But even as Euclid continues its survey, the research results on dark energy are taking a genuinely disturbing turn. Dark energy is losing power. For decades, scientists believed the accelerating expansion driven by dark energy would never stop, that eventually the stars would go out, matter would disperse, and a cold, empty universe would remain, the so-called Big Freeze. One of dark energy's core principles is that the farther apart two objects are, the faster the space between them expands. Galaxies in the Virgo cluster, about 50 million light-years away, are receding from us at roughly 745 miles per second. Galaxies in the Coma cluster, nearly 6 times farther away, are moving away at over 4,350 miles per second. At distances of around 14 to 15 billion light-years, the expansion of space itself surpasses the speed of light, which sounds like it should violate the laws of physics, except nothing can move faster than light within space. If space itself is expanding, the limit simply does not apply. The same way a football field stretching faster than a ball can roll across it means the ball never reaches the far end. This immense cosmic force seemed destined to bring about the eventual cold death of the universe. But recent research suggests a very different outcome might be on the table. The Dark Energy Spectroscopic Instrument, known as DESI, is housed at the Lawrence Berkeley National Laboratory and uses 5,000 robotic fiber optic positioners to study millions of galaxies every single night, building the most detailed three-dimensional map of the universe ever created, spanning 15 million galaxies and 11 billion years of cosmic history. When the DESI collaboration released its findings in March of 2025, the data showed that dark energy reached its peak strength when the universe was 9.6 billion years old, about 70% of its current age, and that its influence has been gradually weakening ever since, now running about 10% below that peak. That means expansion is still accelerating, but dark energy appears to be slowly easing off the gas. By the summer of 2026, the DESI team had strengthened that finding further, releasing an updated analysis built on more than double the previous data set and combining it with independent measurements from the cosmic microwave background, exploding stars, and gravitational lensing, all of which pointed in the same direction, that the simplest explanation, a constant, unchanging dark energy, may no longer fit the evidence. DESI co-spokesperson Will Percival has said, "The team is being guided by Occam's razor, and that the simplest explanation for what scientists are now seeing is shifting, with evolving dark energy increasingly looking like the more promising model, though the statistical confidence has not yet reached the gold standard threshold scientists require to call it a confirmed discovery." Researchers on the project are already preparing a third and final cosmic map, expected to include 50 million galaxies, and take shape by late 2026 or early 2027, which should either solidify this hint into a landmark discovery or watch it fade away the way so many earlier anomalies in physics have. If dark energy continues to weaken, something truly unexpected could happen. Instead of remaining a positive force accelerating expansion, it could become negative over time, its influence reversing, causing the universe to begin contracting, galaxies drawing closer together, space collapsing inward, ending not in a big freeze but in a big crunch, a kind of mirror image of the Big Bang itself. If this data is confirmed, it would be one of the most significant discoveries in scientific history, suggesting dark energy isn't a constant force at all, but something far more complex, possibly tied to physical laws we simply do not understand yet. Current research remains insufficient to say for certain where the universe is actually headed, but one thing is already clear. Our usual assumptions about its future are starting to shift in real time. As scientists try to predict the future of the universe, they are also diving deeper into its past. Using the Atacama Cosmology Telescope, astronomers managed to photograph the universe as it looked just 380,000 years after it came into existence, one of the earliest observable stages possible, since before that point the cosmos was filled with plasma so dense that light could not pass through it at all. After 380,000 years, the plasma dispersed, radiation began spreading through space, and the universe became transparent for the first time, allowing scientists to finally see what it looked like in its infancy. Chaotic clouds of hydrogen and helium that would eventually collapse, heat up, and ignite into the very first stars. The light captured in this image traveled for more than 13 billion years to reach us, and the signal was so faint that the image required a 5-year exposure to capture. Alongside this image, the Atacama Cosmology Telescope gave scientists precise new measurements of the universe's size and mass. The observable universe stretches nearly 46.5 billion light years in every direction from us, with a total mass equivalent to 2 trillion suns, a 2 followed by 36 zeros, yet most of that mass remains hidden. Only 5% is ordinary matter, the stars, planets, and galaxies we can actually see. Roughly 25% is dark matter, and the remaining 70% belongs to dark energy, the mysterious force stretching the fabric of space since the very birth of the universe. These hidden forces don't just shape the universe as a whole, they also determine the fate of individual galaxies, including our own Milky Way. Thanks to the Gaia Space Telescope, scientists discovered that the Milky Way has been a true cosmic predator throughout its history, devouring other galaxies as it grew. On January 15, 2025, the Gaia mission team unveiled the most detailed map of the Milky Way ever created, built from more than 3 trillion individual observations of over 2 billion stars. At the center of that map sits a bar structure hiding our galaxy's dormant supermassive black hole, Sagittarius A star. Rather than the 2 familiar spiral arms most people picture, Gaia revealed that our galaxy actually has several more, including secondary branches, with our own solar system sitting in the outer Orion arm, about 26,000 light-years from the center. Gaia's data also uncovered traces of ancient, long-destroyed spiral arms, ghost structures torn apart by repeated collisions between the Milky Way and its smaller galactic neighbors over billions of years. One of those victims, the Sagittarius dwarf galaxy, has collided with the Milky Way at least 3 times, gradually losing stars and disintegrating with each pass. In 2018, astronomers found direct evidence of these ancient cosmic battles, a group of 30,000 stars moving in perfect sync in the opposite direction from the 7 million stars surrounding them, almost certainly a fragment torn away from another galaxy entirely. A similar collision is unfolding right now, roughly 65 million light-years from Earth, where the galaxies NGC 4568 and NGC 4567 are actively merging into one, offering scientists a preview of what may eventually happen when the Milky Way collides with its closest massive neighbor, the Andromeda Galaxy, currently 2.5 million light-years away. Among the vast amount of Gaia data, scientists also stumbled onto something astonishing: a sleeping giant black hole located just 2,000 light-years away in the constellation Aquila. This black hole carries a mass 33 times greater than our Sun, the first black hole of this size ever discovered inside the Milky Way itself. Scientists named it Gaia BH3. Typically, stellar origin black holes in our galaxy weigh in around 10 solar masses, with the previous record holder estimated at roughly 20 times the mass of our Sun, making Gaia BH3's discovery a genuine leap forward. Its discovery was also an incredible stroke of luck, because it belongs to a category known as sleeping black holes, ones that have already consumed everything within reach of their gravitational field, and now emit essentially no detectable activity. Like Euclid, Gaia also made a major contribution to the study of dark matter and dark energy, though through a different approach entirely. In March of 2024, using its data, scientists completed the largest 3-dimensional map ever made of quasars, the blazing centers of